All right, so today we're going to talk about DeMorgan's theorems. So here is a picture of Augustus De Morgan. He's an old school mathematician. He's best known for his logic theorems in Boolean algebra that bear his name, the De Morgan's theorems. So here is like a snapshot of De Morgan's theorems. And basically what's happening is if you have an inverter going over an or an and, you can break it apart, but when you break this line, you change the sign. So we can look at, so these are going to be the two theorems. Both of them involve breaking an inverter. One of them is we can break an inverter between things that are ORed. We can break it apart. So not A or B is the same as not A and not B. If you think about it, that makes sense, because if you don't have A or B, that means you don't have A and you don't have B. Kind of makes sense. The other one is not A and B. So this says you don't have A and B, meaning you just don't have both of them. That means you can either not have A or not have B. So they both kind of make sense. And now we can look at truth tables. So first, we're going to look at what the theorem is. We're going to look at truth tables to convince ourselves that this is true. And then we'll show how to use that in a simplifying problem. So first, just to kind of look at the truth tables, you can see that if you figure out the truth table for each one, they have the same truth table. And if they have the same truth table, then they're equivalent in logic. So here we got equivalent truth tables for the first one where we're breaking apart an and. So not A and B means you either don't have A or you don't have B. And then if you look at the truth tables for the other one, if it's not A or B, then you either have not A and not B, because you don't have A or B. So you have to have not A and not B. And then again, if you look at the truth tables down here, you can see that the truth tables are identical. 1, 0, 0, 0, 0, 1, 0, 0, 0. Okay, so now we have the De Morgan's theorems that we can use when we're simplifying. All right, so let's look at some examples of simplifying. But first, I kind of already talked about this. The whole idea is if we break the line, change the sign, but don't forget to leave the line over each part that you broke apart. Okay, break the line, change the sign. Break the line, change the sign. So theorem 20 is if we're breaking apart and. Theorem 21 is if we're breaking apart an or. 20 breaking apart an and. 21 breaks apart an or. Okay, so let's do this example. So right here I have an inverter that goes all the way across an or, right? I want to break that line, change that sign. So if I break the line here, then I'm going to have not A. My or has to switch to an and. If I'm breaking the line, I have to change the sign. And then I'm going to have not B. So what theorem did I use to go from the first step to the second step? I broke apart an or, didn't I? So that would be theorem 21. Yeah, I broke apart an or. So this was done using theorem 21. Now, is there anything else I can do to simplify? Let's look back at our theorems. I have not A and not B. And if you look at theorem 9, that double inverter, the not x is equal to x. So theorem 9 says that not b is just b. So we still have not a, and then not b is just b. And if I just write them next to each other, that's the same as writing and. So this is not a and b, and we did that using theorem 9. All right. Any questions on example number 1? All right. So then let's have a peek at example number 2. We have a big inverter and we have an and, right? We have this left chunk and this right chunk. And if we didn't have the DeMorgan's theorem, we would have to like FOIL this and multiply everything out and then start messing with stuff. But since we have DeMorgan's theorem, we can break this line and change that sign. So we're going to use theorem, the one that breaks apart multiplication is theorem 20. So we are going to use theorem 20 to break apart that multiplication. So then we are going to have an or in between these parentheses, right? So we're going to have P and not Q, or not P or S. And then each one of these still has the line over it. So then, now what can we do? We used theorem 20 to break apart the and. Now we have, it looks like we have two theorem 21s. We need to break apart an or here and an or there. So I'm going to do theorem 21 twice. Take a look at theorem 21. That's where you break apart an or, and you break the line and change the sign to and. So I'm going to break this line. I'm going to change that sign. So break the line. I'm going to have not P and not Q. Or break this line, change that sign. Not P and not S. Then I got two double negatives here, right? I got not Q and not P. So that means I'm going to use theorem 9 twice to get rid of those double negatives. So not P and Q, or P and not S. And that's all we can do there. There's nothing we can factor out. We don't have any of our theorems, so we're done. All right, let's take a look at the next example. So we have got a big old inverter up here and an and. So breaking apart an and, that is theorem 20. So we're going to break this line and change that sign, which means we're going to have an or in here. So then we have not x and not y. Got to be really careful paying attention to how many of these lines we got, right? So you look above each letter. X has 2 lines above it. Or no, yeah, x has 2 lines above it. I should have, and I do, I have 2 lines above x. Y has 3 lines above it, so the y has 3 lines above it. Good. Then over here, we've got not y and z. All right, and we did, that was theorem 20. All right, we have, over on the left side, we have a not, right? These are right next to each other. So these two here are going to get theorem 9. So those will kind of cancel each other out. So let's do that. So the not will make each other go away. So we just have x and not y, or not y and z. And then we have a big not over an and here. So breaking apart an and is theorem number 20. Oh, so the other one, when we break apart an or, it was 21. So we didn't break apart an or. We're just breaking apart ands here. So we're going to do another theorem 20 on the second part here. So I'm going to break this line and change that sign. So it's going to, instead of and, it's going to be an or, and I'm going to have not y. And then here we have not z. And that was theorem 20 again. And then we've got a double negative on the y. So we can use theorem 9 to get rid of that. So we have x and not y, or y, or not z. And if you look at these first 2 terms right here, you can see we have a y and a not y, and one of them has a partner, so that we can get rid of the one that has the partner. That's one of our consensus theorems. So we have y and not y, and then the not has an x with it. So let's see which of our consensus theorems it would be. We had y and not y, and then we had so it looks like we have theorem 16, but just with the x and y switched, right? We have y or not y and x. So we're just going to cross out the not y. And that's theorem 16. So we got consensus theorem here that's going to make, we're going to use theorem 16, which is going to make this y cancel out. So then we have x, that not y, the not y cancels out. or y or not z. And then there's nothing else we can do to simplify that. So any questions on that one? Okay. And we got one last one. So, so the last one we're going to do is we're going to say, all right, well, first of all, where do these weird, we haven't seen this weird of Boolean expressions yet, right? So we're going to look at a circuit that gives us a weird one and then see how we can simplify it. So if we look at this circuit, we got this AND gate right here. We got X and Y as inputs. So coming out of that AND gate will be X and Y. Then going through the inverter, we'll get not X and Y. Then that is going to go into this AND gate. So we need to figure out what's coming into this AND gate. So we need to do down here. So this inverter has X going into it. So coming out of it will be not X. So then this OR gate would be getting not X or Z. So over here we'll have not X or Z. This AND gate is just going to AND this and this together. And we can write that with parentheses, right? And then the inverter is just going to put a line over the top of both of these. Like that. So now what we're going to do is we're going to simplify. We're going to simplify that expression. We're going to change these to 4s. And here we go. All right. We've got an inverter over an AND. So that we're going to break the AND with theorem 20. Breaking apart the AND. So I'm breaking this AND apart, so it's going to end up with an OR. Break the line, change the sign. So we've got not X or Z. And then on this side, not X and Y. And that was using theorem 20. All righty. Now on this part here, we can use theorem 21 to break apart the OR. So let's use theorem 21 to break this sign, or break this line, change that sign. So we're going to have not X and not Z. Or not X and Y. And that was using theorem 21. Let's see, we've got a couple of double negatives here, so we can use theorem 9 to get rid of the double negatives. Not X is X. So we get X and not Z. Or these two undo each other and we just have X and Y. And they said to leave our answer in sum of products. So we don't want to factor out the x. That's all we can do there. All right. I am going to stop the recording now.